So we talk about reaction and reactants as well as reaction rate. We talk now about where do they happen. So there are mainly three kinds of reactors. They are called ideal reactors because we assume the ideal conditions here. But these ideal reactors can be used in many in solving many problems in real world. Though it's an ideal case, but we can assume some of these processes. So batch reactor is more of a sequential inflow, mixing and then discharge of effluent. It means that it's not a continuous mass flux in. No, you just input the mass, leave it there, make the reaction, and then after some time, you discharge. That's it. So it means it's by batch. After discharging, you can input another new one. So it means it's by batches. So there's a reaction there. As I mentioned, this is unsteady state condition in most cases because once the reactant is put here, what happens? The concentration is changing through time. All right. So the changing through time. So it means that it's not. It is a steady condition, a steady state. Now, the second reactor is what we call as continuous stirred tank reactor, or CSTR, or the other name is completely mixed flow reactor, or CMFR. They're the same, all right? CSTR or CMFR in this case. So in many environmental processes, this is what is happening. There is a mass flux in, and then there's your control volume there, the container, and then there's a mass flux out. So this is consistently going in, continuous inflow, outflow, and mixing. So in this case, there's an inflow, which is the volume flow rate, and we have the concentration, initial concentration. You have the effluent, which is the outflow here, volume flow out, and then the final concentration. And then inside here there's a continuous mixing. It means that you use a stirrer there and you continuously mix. So once you put inside the concentration C sub O here, it goes inside. Because it's continually mixing, what happens? At this stage, this concentration, because of the continuous mixing, just like when you are making coffee, if you put the powder in the on the hot water, if you mix it, the assumption is that in any part of the cup, the concentration is the same. All right? Because you are perfectly mixing the whole concentration. So if you go below the cup, from on the top of the cup, it means that the concentration is the same. It's the same thing in this case here. So if you get the concentration from here, if you get the concentration from here or from here, it's all the same concentration. So that is why in the continuously stirred tank reactor, the concentration at the reactor is the same as the concentration of the effluent. Okay, so in this case, C sub T is equal to C, right? Which is C is here because of continual mixing. So there's a good mixture already. Yeah. The next reactor that is usually also commonly seen in environmental systems is plug flow reactor, PFR, or sometimes it could be a continuous tubular reactor or CTR, but normally it's plug flow reactor. So what is a plug flow reactor? This system is completely unmixed or perfectly unmixed reactor. What does it mean? So if you try to see, this is reactor that is used usually for pipes. There is a high aspect ratio. It means that the length is much longer compared to the width in this case. What happens is that if this is a pipe here, you have an example here. You have an influent coming in. The influent has a flow rate of Q in and a concentration of C sub O. All right? So it goes in, but it acts like a piston. So just imagine you have a piston here, and the piston is being pushed. You push the piston, so it means the fluid at the front of the piston will also push together, right? So once it pushes, it means that for a plug flow reactor, the small area or cross section of this part here, let's say this part here, and this part here, and this part here, they move together. and they don't mix together. So it means that the concentration at this part is not equal to the concentration of this, is not equal to the concentration of this. In most cases, in many cases, usually, the concentration at the inlet side is higher than the concentration at the outlet side because it's becoming smaller concentration. But the concentration of this area 1 and 2 and 3 are not the same. It's different. All right? The assumption being in here, this part here, the small plug, as we can see, the small volume here, we are saying that there is no radial, no axial mixing. This part here is not mixing with the other neighboring part. They only mix together to the radially. This part here, they mix together at only this stage, only this part, radially. All right? So this is the mixing only at that specific point. But this part here, if we have another one here is a different concentration. They don't mix together axially, all right, through the axis. They don't mix together. So this is good for assumptions of many environmental process. Like for example, if you're talking about fluid flow in pipes or even in groundwater, because this one will make it simpler. But in reality, of course, there is a little bit of axial diffusion in reality. But we can always assume in a plug flow reactor to be no mixing at all right? To make it ideal case in this case, to make it simpler way of solving some of the issues in different kinds of reactors, all right? So to recap, we have batch reactor, we have CSTR or CMFR, and we have a plug flow reactor, all right? So these are the three types of reactor, okay? We can have this one as a closed system. Normally for the batch reactor, we have closed system, and for these two, we can have some open systems. It doesn't matter because we can have inflow and outflow as well. Okay. So these are, I think this one I have mentioned earlier. It can be used for waste treatment in lagoons, okay? We can use a lagoon as a way of a batch reactor or a tank, like for example, water tank. So if we have a water tank, we can make this one as a batch reactor. So in the water tank, if we put some chlorine, okay, batch. So this one, if you put some chlorine, there is some reaction there. So you can make this as a batch reactor. And then for completely mixed flow reactors, we have a lot in wastewater treatment plants. We can also model some lakes. There is some flow. We can also equalization and mixing tanks in wastewater treatment plants. All right, so we can have that one as a model for, as a CMFR model for this kind of processes. For plug flow reactors, we can use that one for, especially for pipes, all right? Some pack tower biofilters, like a tower type, and also some long, narrow rivers, we can also designate as plug flow reactor in order to solve some of the problems there. All right, so let's try to analyze this reactor based on the various orders. So based from the mass equation, mass balance equation, we have the mass accumulation is equal to the mass flux minus mass out plus minus RV. But in this case, for batch reactor, there is no input and output, right? As I mentioned before, you just put the thing here, and then it remains there. So it means the mass flux is not continuous. So you can make this a 0. And there is no mass out. The mass out is 0 as well. So it becomes 0 as well, right? So now it's 2 zeros. And then the mass accumulation is now a function, or is now related to only to the reaction rate here. So for first order reaction, we can say that the R here, for the reactant here, is first order is minus Kc, right? As you mentioned before, R for the first order is minus Kc, all right? So in this case, the R becomes minus Kc, all right, times V is equal to the change in accumulation, all right? if we make this one, because the volume is constant, so the V here, the volume of this reactor is constant. So this is a constant volume here. So you can cancel out the volume, this part here and this part. So what happens is, only the remaining is dC over dt is equal to minus kc. All right. So now we have the formula or the equation for a batch reactor based on the concentration. So now if you try to integrate this one, okay, so you have dC, all right, it becomes minus kc dt, right? And then c can also be put here. So it becomes the integration now will get you the equation, okay, the integrated equation of the for a reactor analysis for a first order reaction, in this case for a batch reactor. Okay, I will show you now the integrated equation after a few slides. The same way for a CMFR. So for the batch reactor, we don't have mass flux in and we don't have mass flux out. For the CMFR, we have a mass flux in and we have a mass flux out. All right. So in this case, usually for a CMFR, it's a steady state condition. All right, a steady state condition with reaction. So in this case, the mass flow in Qi is equal to the mass flow or the volume flow rate out in a steady state condition. So Qi is equal to Q out. And as I mentioned to you before, the concentration of this reactor here is the same as the concentration of the output concentration. All right, so CO is equal to the concentration at C. All right, so now we can simplify things. All right, so we have the change in accumulation, which is the same here, is equal to the CI concentration, initial concentration, times the volume flow rate, which is the same. Qi minus Q is Q is the same, minus CO minus KCV. All right, KCV, where C and CO are the same. All right, so based from here, we can also make integration based from this formula, which I will show you. The integration, the way to integrate and everything like that, I will not show here. You can do it on your own, but I will show you the integrated formula already at the end of this slide. In the same way for plug flow, we can also do the same for plug flow. And so for a plug flow mixture, there are two assumptions. No element or fluid in the plug reaches the end of the reactor before any other. So it means that this element here will not reach before or faster than the element here. So it means that that element here, this part here, will reach the outflow first, then the next element, then the next element, because they are all not mixing. All right, and then the result in the same residence time in the reactor. The residence time is the time that is the reactant is maintaining or is within that reactor. Okay, the amount of time of the reactant inside the reactor. All right, so we will show you this one now for various equations for various reactors. So now after integration, we can see these types of formula now. All right, so this is a table. We have ideal batch reactor, we have ideal plug flow reactor, and we have ideal CMFR, continuously mixed flow reactor. All right, and CT is the concentration, the final concentration. So if you look at this part, where is CT? CT is CO, this part, the final concentration of the outflow. All right, so that is the CT here. So after we have integrated, I go back here. If we integrate this part here, all right, integrating this equation here will result to this equation for ideal batch. Okay, what does it mean? For that, it means that CT, this is the CT here. When I put here, okay, let's see from here, CT is equal to CO minus KT. All right, so this is the meaning of that equation in this part here. All right, so CT is the final concentration, is equal to the initial concentration minus the constant, reaction rate constant times the time. All right, that is for the ideal batch reaction, a reactor, I mean. The ideal plug flow is the same. CT is equal to CO minus K theta. Theta here is what we call as hydraulic residence time because this is flowing. Okay, so this time is not flowing, right? You can see that there's a T here. The T there is just the residence time within the reactor because it's not flowing. There's no inflow, there's no outflow. But for the CMFR, there is an inflow and outflow. So the residence time, it is the time, the amount of time that is staying inside the reactor is what we call as theta. All right, so this is the hydraulic residence time. So it's still time. The unit is still time for that one. So in that case, you can get theta. So theta, you can also get theta is residence time is equal to volume over the Q, right? Volume flow rate, right? So if volume is liters, volume is liters per second, right? You can get second. So this is theta is second or days or hours, right? So you can get this one as theta as the residence time for this part here. If you are given volume and you have volume flow rate, you can get the residence time. The same way for ideal, sorry, that is plug flow, sorry. That's plug flow. It's pretty much similar with the CMFR anyway. So this one is the CMFR, CO minus K theta is for CMFR. This is for plug flow, okay? That is for the zeroth order of reaction. For the first order, we have minus Kc as the reaction rate, all right? So we have now CO, CT is equal to CO E raised to the minus KT. Okay, this part is the same, all right? So now CT is equal to C sub O E, okay, to the minus KT is for the ideal batch. This one is for the ideal plug flow. CT is equal to CO E to the minus K theta. And for ideal CMFR is CT is equal to CO C sub O over 1 plus K theta. All right. So these are the various equations for different reaction orders as well as different reactors. And for the second order as well, you can have this kind of equation. All right. So for steady state condition, as I mentioned before, you can also get the retention time. If you have the hydraulic retention time can be used theta is equal to V over Q, or sometimes if you are given the various concentration and the reaction constant, you can also solve for theta using this formula. It's basically this all equation are basically coming from the same equation here, only that it's theta. They are solving for theta instead of C sub T. So it's basically the same equation as before. Okay, so now we have the various equations and the various reactors that we usually use in environmental processes. So this is example of what happens, of the way a relationship between concentration and time. This is concentration versus time, concentration versus time. You can see from the zero order reaction in a batch reactor. So this is example of a batch reactor, right? What happens? So the zero order reaction for a batch reactor is independent of the concentration. So it means that regardless, the reaction rate, all right, is constant here. So it's just degrading consistently through time. So the concentration is the same reaction rate throughout. So the concentration is just decaying consistently in a linear manner because the reaction rate is constant. In this case, first order, the reaction rate is in proportion to the concentration of the reaction, or of the reactants, I mean. So the higher the concentration of the reactants, the higher the reaction rate. So in this case, because at first, initially you have high concentration of reactant, so the reaction rate is higher. And then eventually, because the reactant concentration is slowly decreasing because it is being used already, So it means the reaction rate is slowly decreasing through time, right? You can see from this graph here, it's slowly decreasing through time because of the decreasing amount of concentration as well. So the reaction rate is proportional to the concentration of the reactant. In the same way, for the second order reaction, there is a steep decline in concentration at the initial stage because the reaction rate is proportional to the square of the concentration, right? So the higher the concentration, the higher the reaction rate. So that's why for a second order reaction, you can see a steep decrease of concentration. And once the concentration decreases, also the reaction rate decreases through time, right? Because the lower the reaction, it is proportional to the concentration. So now it is decreasing through time because this is lower concentration now.